All right, so thank you so much for the invitation. So as was mentioned, this paper is joint with Drew Fudenberg at MIT. And the paper is about using machine learning to help us achieve not just better predictions, but also potentially better understanding into a given domain. All right, so there's been a lot of talk about machine learning. Many of the applications have been in the context of prediction problems. So there's some outcome of interest that we want to predict, and we have access to a large set of features. Okay, so the techniques for machine learning are very productive towards this goal of predictive accuracy. But the methods that are used are often notoriously black box. Right, so that's fine for many applications, but from the point of view of research or from a modeler's perspective, it might not be fully satisfying. And so Drew and I were curious about whether we could use these techniques not just to help us achieve better predictions, but also potentially to teach us something about an underlying domain. Okay, specifically, that might look like using machine learning to help us identify new patterns, or using machine learning to help us build upon existing models. From this perspective, machine learning really need not be seen as a sort of substitute or replacement for traditional modeling. It might actually serve as a complement to these techniques. Right? And in our paper, what we do is we focus on a particular domain in which we can ask these questions. And that domain is predicting initial play in games. So I wanted to mention there's been some very nice work by Kevin Layton Brown and James Wright for this problem as well. All right, so the specific prediction task we look at is the following. Okay, I'm going to give you a 3x3 payoff matrix. Those are your features. And I want you to predict the action that is most frequently chosen by subjects acting as the role player. So it's a classification problem. I'm going to assess the accuracy of your model using the correct classification rate. So simply, in what fraction of games is your predicted modal action, in fact, the true modal action in our data set? And throughout, I'm always going to report for you tenfold cross-validated prediction errors, so everything is going to be an out-of-sample test. All right. So this is an old problem in game theory. There are many models one could use for the prediction task we've outlined. And what we're going to ask is whether we can use machine learning to improve our understanding beyond those existing models and potentially to build extensions of them. So the paper is going to unfold in 3 parts, okay? And I'm going to give you a quick outline of these 3 different parts, and then I'll go through these in more detail slowly. Okay. So in the first part of the paper, what we do is we look at instances, meaning games, where machine learning predicts well, but the existing models don't. Okay, so those instances are particularly interesting because the fact that the machine learning algorithm predicts well means that there's some sort of regularity there, while the fact that the existing models don't suggests that that regularity isn't yet captured by the existing models. So we look at these instances, and from them we're able to identify a single parameter extension to our best model, which then achieves the performance of the black box. Right? After that, we then try to break this best model. So we go beyond the data set that we initially had in part 1, and we use machine learning to help us algorithmically design new instances of games that we then get data for. Okay, we then find a model that fits these new games better than the model we identified in part 1. And then finally, we loop back and use machine learning to bridge these 2 models in a sort of hybrid model, where initially the algorithm helps us choose between which of these models we want to use for prediction. Okay, so again, that was fast. Let me now go through these parts slowly. All right, so we begin with a data set of 86 symmetric 3x3 normal form games. And this is a metadata set that was aggregated over 6 different lab experiments, and the original sources are here. We have 40 to 147 observations per game. Okay, each of these observations is really initial play, so there's no learning and no repetition. This data set was aggregated by Kevin and James, whom I mentioned earlier. All right, so we're going to consider 2 different models for predicting play in these games. The first model is built on Nash equilibrium. Right, so we can simply, of course, predict an action that is consistent with pair strategy Nash. If there are more than one action that has that property, we can predict uniformly at random from those actions. The second model that we consider is a leading model from behavioral game theory, so it's called the Poisson cognitive hierarchy model. And let me just very heuristically give you a sense of what the model does. So it says that there's potentially multiple different levels of sophistication that players can exhibit. So level 0 would be a maximally unsophisticated player. This player is just going to choose from his actions uniformly at random. A level 1 player is a little bit more sophisticated. That player is going to act as if their opponent is level 0, and best respond to that level 0 opponent. And then we can then recursively define higher and higher levels of sophistication. Okay, this model assumes that there is a Poisson distribution over these different levels. And that distribution has a rate parameter tau, which is the single free parameter of this model, which is then estimated from the data. Right, so how do these models perform on our prediction task? So throughout, I'm going to show you these prediction accuracies relative to two benchmarks. One benchmark is completely naive prediction, or you can always guess at random. And that's going to give you an accuracy of 1/3. On the other extreme, if you have access to the test set, then you should be able to predict the modal action 100% of the time. So here are the accuracies from the two models. And what we see is that both models improve on guessing at random. So uniform Nash correctly classifies the modal action 42% of the time. PCHM really does quite well. It correctly classifies the modal action 72% of the time. Okay, additionally, when we estimate this free parameter tau from the data, this more complex model actually collapses to just prediction of the level 1 action. So it's as if game by game, we simply found the action that was the best response to uniform and predicted that action. So throughout, we're actually just going to ignore the more complicated model PCHM and work with this simpler model level 1, which equivalently achieves this accuracy of 72%. So those are the standard models. Let's now try a machine learning approach. And we take really just a cut and dry machine learning approach where we identify each game with features that we think are strategically relevant. So just to give you some examples, for each action, we define indicator variables that capture certain strategic properties of the actions, like, is it part of a pure strategy Nash equilibrium? Okay, is it part of a pure strategy Pareto-dominant Nash equilibrium, by which we mean the payoffs in that Nash equilibrium Pareto dominate the payoffs in all other pure strategy Nash. Okay, is it level K? Is it part of a profile that maximizes the sum of player payoffs, and so forth? Then we train a decision tree ensemble to predict the modal action given access to these features. And we find that that ensemble improves upon the existing models. Okay, it doesn't actually improve by a whole lot, so we're getting to 77% accuracy, okay, but it is an improvement, and therefore we can ask, where is that improvement coming from? So what we do to answer that question is we find those games that are correctly predicted by the decision tree ensemble, but not correctly predicted by the level 1 model. One example of such game is the one I have up here. So in this game, action A1 is a level 1 action. It has the highest expected payoff against uniform play. But if you look at action A2, it has almost as high an expected payoff against uniform play. And additionally, it leads to lower variation in the payoffs that you might receive. So in this game, although A1 is a level 1 action, the action A2 is actually the action that is most frequently chosen by row players. And this is a regularity that we find in all of the games where the modal action is correctly predicted by the algorithm and not by level 1. So this looks quite familiar. It essentially looks like risk aversion. And risk aversion is something we can take and port back into the level 1 model. So what we do is we just extend level 1 by supposing instead that players have a utility function described as follows. Okay, X is the payoff, and alpha now is a parameter that governs the degree of risk aversion. This adds one free parameter to the level 1 model. We're going to estimate alpha on the data, test it out of sample, and this extension of level 1 actually achieves, even weakly improves upon the performance of the decision tree ensemble. So what we take away from this is, maybe we don't like the black box algorithm as the end output. Nevertheless, we might be able to use it in some cases to lead us to interpretable parametric extensions of our existing models. All right, so we could have stopped here. The level 1 alpha model is achieving correct prediction 80% of the time. That sounds pretty good. All right, so we might say, look, we're just done. That's an almost complete model of play. The catch is that the data set that we're using, these lab games, are actually really special games. So these are games that were designed by experimental game theorists to achieve certain experimental goals. And we might worry that the performance of level 1 alpha is due to those properties. So to test that, we really need to see play on new kinds of games. And then this brings up a question of what kinds of games do we want to look at. So even in the space of 3x3 payoff matrices, there's just a very large number of games we could try to get data for. And so the first thing that we do is we actually try something sort of naive. We just generate payoffs uniformly at random. This turns out to still generate special games. These games are special in the sense that they're strategically very simple. They tend to have a small number of Nash equilibria. Many of them have a strictly dominant action. And as a result, we actually find that level 1 alpha performs even better on those randomly generated games relative to the lab games. So if we want to be able to discover a part of the game space where level 1 alpha doesn't do so well, we actually need a slightly more sophisticated procedure for game generation. And that's what we do in the second half of the paper, second part of the paper. So we use machine learning to try to help us find cases that will break this model. Right, our procedure is as follows. We begin by taking our data set of games in observed play, and we train an algorithm that takes as input the payoff matrix and outputs now no longer a prediction of the action that is taken, but instead a prediction of the frequency of play of the level 1 action. Then we can take that algorithm, again generate new games at random, now use that algorithm, apply it game by game to generate a predicted frequency with which players will play the level 1 action in that game. We set 50% as a sort of arbitrary cutoff, where we decided that more than 50% was just a lot and less than 50% was acceptable. And we took all of the games where the predicted frequency of play exceeded 50% and we dropped them from our data. Then we repopulated those instances with new randomly generated games, again applied our algorithm to predict the frequency of level 1 play, and just repeated this procedure until we had 200 games that were all predicted to have relatively low frequencies of level 1 play. Then we took those 200 games, elicited play on those games on Mechanical Turk. Right. First, just note that there's no guarantee, of course, that level 1 play is actually going to be low in these games. It's just that the algorithm thinks that'll be the case. Right. So the first thing we verify is that, in fact, it achieves that goal. So remember, level 1 alpha was achieving an accuracy of roughly 80% level 1 alpha, 80% in the lab games, and actually in the randomly generated games, the first time it was about 90%. And here we see it really plummet, so the performance on these new algorithmically generated games is about 40%. So that's not to say that there isn't structure in these games. And if we look at a decision tree ensemble, that's achieving 73% accuracy. Right? So there are regularities in these games. It's just that those regularities aren't captured by the level 1 alpha model. So what are those regularities? Okay, what we do here is we actually directly look at the decision tree itself. Okay, we don't want to look at the ensemble because that's really a nightmare. It's just huge and difficult to interpret. But we can look instead at a very constrained version of the ensemble. And by constrained, I mean we're going to look at a single decision tree, and we're going to force it to have just 2 splits. Okay, so the best 2-split decision tree turns out to look like the following. So it begins by asking whether action A1 is part of a Pareto-dominant Nash equilibrium. If so, it says to predict that. If not, it says to ask whether action A2 is part of a Pareto-dominant Nash equilibrium. If so, predict that, and if not, predict A3. So this is very interpretable. It basically looks like the algorithm wants us to predict the Pareto-dominant Nash equilibrium. So we didn't really like the ordering of actions used here, but we took that and had it motivate instead this very related rule. We're going to call PD&E the rule that predicts at random from all actions that are consistent with some Pareto-dominant Nash equilibrium, and otherwise predicts at random from the available actions. Okay. And this simple PD&E rule turns out to achieve a large part of the improvement of the decision tree ensemble over the level 1 alpha model. Now, that's not to say that PD&E is now discovered to be a better model than level 1 alpha, because remember, this again is a very special set of games. Right? There's this tendency sometimes to want to run these horse races between models and say model A is better than model B. But what we really take away from that is that there's not necessarily a lot of meaning to that, because the ranking you're going to get is very particular to the specific game generation process that generated your data set. Right? So instead of forcing either PD&E or level 1 alpha to be a sort of universal predictor of play, why not actually try to merge these and accept that they're both good models, they're just models, good models of play for different kinds of games. Right? So that's sort of further evidenced in this table. So here we aggregated all of our games, the lab games, the randomly generated games, and our algorithmically designed games. And you see that sort of both models do well, but neither is really the complete story. Right, so in the final part of the paper, which I'll just do very fast, essentially we try to use machine learning to help us decide game by game which of these two underlying models we want to use for prediction. So first, what we do is we take our training data, and we train for each model a decision tree, which takes as input the payoff matrix and outputs a prediction for the accuracy of the associated model. Okay. Then, for a new instance, what we can do is we can take that game, run it through these two decision trees associated with the two models, output a predicted probability of accurate prediction for each of the models, and then simply go with whichever model is predicted to have a higher probability of accurate prediction. So this hybrid model, right, so here are the accuracies I've shown you previously. Right, so level 1 alpha achieves 68%, PD&E achieves 56%. And the hybrid model really blows these out of the water. It achieves an 80% prediction. Right, so I want to point out that this more complex model wasn't guaranteed to improve upon the two component models because these are all out-of-sample tests. And also, especially, the extent of the improvement is also not guaranteed. Okay, now this improvement is also special, again, to this data generating process, and how much we expect the hybrid model to improve would depend a lot on which game generation process we used. Okay, so let me just conclude. So in the paper, we also look at how the model assignment is done, and we learn a few things from that, but let me skip that here. Okay, so then just to conclude, we can sort of roughly think about models as living in this space where we evaluate them by their interpretability and also by their predictive accuracy. Okay. Traditional economic models tend to be high on interpretability and predictive, but maybe not the most predictive. Okay. On the other hand, we have black box algorithms, which are highly predictive, but potentially very low on interpretability. Right. Now, there's some sort of trade-off between these two goals, but potentially there is another model class out there that's roughly as predictive as the black box algorithms and not that much less interpretable than our traditional models. Right? And if there is a model class like that out there, we sort of want to know what it is. And this paper really has been about how we might be able to search for that model class, making use of the black box algorithms. Right. Thank you. So should we do questions, or should I pass it on, or are we doing questions?
We'll do questions.
Okay,
let's do a few questions while the people is getting ready. We have one there.
So I'm not sure I understand the question. So we basically took the ensemble that we had trained, and we looked at the cases in which it predicted correctly. Right. So yeah. So essentially, we can look at, right, for each game, we can output whether it was correctly predicted by level 1 and whether it was correctly predicted by the ensemble, and then look at the cases that have the property that it's correctly predicted by the ensemble and incorrectly predicted by level